Welcome once again in the class of topology, and in some previous videos we are doing the chapter of compactness, and in previous 2 or 3 videos we have done a little bit about countable compact topological spaces, and one more theorem remains about the countably compact topological spaces, and then we will move on to the sequentially compact topological spaces. But before moving on to that topic, let us complete the topic of countable compact topological spaces. So the first theorem I am going to take today. So just write down the statement of the theorem first, and then we will move on to the proof. Statement is that every closed subset of a countably compact topological space is itself countably compact. So that means if a topological space X tau is countably compact and we are having a closed subset f of X, then f itself will be countably compact. That what we are going to prove in this theorem. So you must have written the statement, and now we are moving on to the proof of this theorem, which is really very easy. So for the proof, let X tau be a countably compact topological space. So we have taken a countably compact topological space, and we will take a closed subset of it. So let f subset of X be closed. So f is a closed subset of a countably compact topological space X tau, and now we are to show that this f is itself countably compact. To prove that f is countably compact, what we will have to do? We will have to take a countable open cover of this f, and we will obtain some finite subcover of that countable open cover. So let C be a countable open cover of f. Let C, and member of C I am taking as G1, G2, G3 and so on. Let this be a countable open cover of f. To show f is countably compact, we will have to find a finite open cover of this countable open cover. Since C is countable open cover of f must be a subset of union of members of this open cover. So you can write Gn where n belongs to the set of natural numbers. So f is a subset of this, and take union on both sides with complement of f. So here you will get f complement, here you will get this set union with f complement. But what is f union f complement? It is the whole set X, the whole topological space X. X is a subset of this, and since X is the whole space, you can replace this sign of subset by equality. So X is equal to union of all members of this cover C union with f complement. That means, and f complement is also open because f was closed. So that means this set f complement and a collection of all those Gn's where n belongs to n, that means G1, G2, G3 and so on. This collection, name it as C1. So this C1 is a countable open cover. This is a countable open cover of X. But X is given to be countably compact. Since X is countably compact, so every countable open cover of X must have a finite subcover. So this is a countable open cover of X, so it must also have a finite subcover. So therefore there must exist a finite subcover, finite subcover of this C1. Say the members of this subcover C1 star, let them be F complement. I'm taking it because it is a single member, will make no effect on the finiteness of this subcover. And then some finite number of members from Gn. So I'm taking renaming them as Gm1, Gm2, Gm3, and so on, Gmp. So these are the finite number of members from this cover C1 that will form a finite subcover of C1. Since it is a finite subcover of C1, the union of members of this subcover will definitely cover X. So X will be union of F complement and union of these members. And these are, you can write these as G, M, J, where J vary from 1 to P. And X can be written as F union F complement once again. So F is a subset of this also. So F is a subset of F union F complement, and F complement, F union F complement is equal to this. So you can directly say that F is a subset of F complement union GMJ, where J is varying from 1 to P. And one thing is clear, that no part of F is covered by F complement. So you can remove F complement from the right hand side very easily. So that means F is a subset of these P members of that cover C1, but these are also the members of C. So that means these members, so this means this set GM1, GM2, and so on, GMP, this is a finite subcover of C. This is a finite subcover of C. And what was C? C was an arbitrary countable open cover of F. So for the closed set F, we have seen that every countable open cover of F is having a finite subcover, and that makes this set F a countably compact set. That means every closed subset of a countably compact space is itself countably compact. So this was the first theorem we have covered today. Now we are moving towards the topic of sequential compactness of topological spaces. So first I will define what is sequential compactness, and then we will cover one or two theorems based on sequentially compactness, and then we will move on to the topic of local compactness. But first we are moving towards sequential compactness. Sequential compactness. So first of all, the definition. When a topological space will be called sequentially compact. So a topological space X tau is said to be sequentially compact. Sequentially compact if every sequence in X has a convergent subsequence. So this is the definition of sequentially compact topological spaces. A topological space is sequentially compact if every sequence in it has a convergent subsequence. So this is the definition, and now we are moving towards some theorems. First of all, there is a very easy, very basic, very fundamental theorem based on sequential compactness, and the statement of the theorem is, write down the statement first. If X is finite, then the topological space X top is sequentially compact. Here, whatever the topology tau may be, whatever the topology tau you can take cofinite topology, you can take co-countable topology, you can take discrete topology, you can take indiscrete topology, or whatever the topology you want to take, you can take. But if X is finite, X top must be a sequentially compact topological space. This is our first theorem based on sequential compactness. And the proof is very, very easy. You can say trivial proof. So I'm moving towards the proof now. Let X be finite. Let X be finite and let Xn be a sequence in X. What we have to show that this sequence Xn has a convergent subsequence. Now, Xn is a sequence, so how many terms will it contain? Definitely infinitely many. But from where these terms are coming? They are coming from the set X, which is a finite set. So finite set and infinite number of members of the sequence are coming from the finite set. That means definitely at least one member will be there of this set X, which will repeat infinitely many times in the sequence Xn. So let it be A. So let Xn1 be A, where n1 is least natural number to satisfy it. So starting from 1, x1, x2, x3, first time when A will be there in the sequences, the n1th stage, so xn1 will be A. Let the next time when A comes in the sequence, it is xn2. Let n2 greater than n1 be such that xn2 is A, and so on. Then xn3 will be A, then xn4 will be A, then xn5 will be A, then xn6 will be A. So this A will be there in the sequence infinitely many times, and this sequence xni, this is a constant sequence and it will converge to A, because each term of this sequence, this subsequence, is equal to A. So for this sequence Xn now, you are having a convergent subsequence which converges to A. And this is happening, why? Because the set X is finite and at least one of the members of this finite set will repeat infinitely many times in the sequence Xn. What you have proved now? You have taken a sequence and you have obtained a convergent subsequence of it. That means your topological space is sequentially compact. So this was the first theorem, which was trivial, which was easy, which was very simple. And now we are moving towards another theorem which is not so easy. It may take time, may take your brain. So what the next theorem is? Write down the statement first. Theorem. We have done the topic of countably compactness. We are doing sequentially compactness, and the theorem is interrelated. The statement of the theorem is every sequentially compact topological space is countably compact. That means if a topological space is sequentially compact, then it must also be countably compact. And this term we are going to prove. So what we are to start with, from where we are to start with? We will take one sequentially compact topological space extra, and then we will show that it is also countably compact. So let X tau be sequentially compact topological space. We have taken a sequentially compact topological space and then we will show that it is also countably compact. So we'll prove it by the way of contradiction, by the method of contradiction. First we will suppose that it is not countably compact and then we will arrive at some contradiction which will mean that our supposition was wrong and hence it will be countably compact. So suppose on the contrary X top is not countably compact. Is not countably compact. It is not countably compact. We have supposed. What was the definition of countably compact topological space? That every countable open cover has a finite subcover. And since we have supposed that it is not countably compact, definitely there will be a countable open cover having no finite subcover. So therefore, there exists a countable open cover and let it be Gn where n belongs to n. That means G1, G2, G3 and so on. This is a countable open cover having no finite subcover. So this countable open cover is having no finite subcover. That we have supposed because we have supposed that it is not countably compact. Now let us see what it means. It means that finite number of members of this collection, they are not able to cover the topological space X. One more thing, that there will be several GIs, GNs which will be intersecting X. There will be several which are not intersecting X. So suppose we will form a sequence. Now what we are going to do, I'll give you a picture first. I'll try to find a sequence having no convergent subsequence. That means I'll try to prove that it is not sequentially compact, and that will be the contradiction because we are given that the topological space is sequentially compact. So let M1 be the smallest natural number such that X intersection with GM1 is not phi. And if it is not phi, then definitely you can have one member from this set. Let it be X1. So let X1 be a member of this X intersection with GM1. Now suppose M2 be the next natural number such that X intersection GM2 is not phi. Let M2 be the next natural number such that X intersection with GM2 is not phi. So you can take, since it is non-empty set, you can take one member X2 from it, and I am taking X2 in such a way that X2 belongs to this, but X2 is not in this X intersection GM1. So choose X2 belonging to X intersection GM2 such that it is not in X intersection with GM1, and it is possible. Why it is possible? Because if it is not possible, that means the space X is covered by a single member GM1, and we are saying that X is not covered by finite number of members of this cover. So it is always possible to choose one X2 which belongs to X intersection GM2 and is not in X intersection GM1. Similarly, let M3 be next natural number such that X intersection GM3 is not phi. Once again, this set is not phi, this is non-empty. So definitely there will be some elements in this set, and choose x3 from this set such that x3 is in this set, but x3 is neither in x intersection gm1 nor in x intersection gm2. So choose x3 belonging to x intersection gm3 such that it is not an intersection of x intersection with gmj, where j vary from 1 to 2 now, because I want x3 in x intersection gm3, but I want x3 not belonging to x intersection gm1 and x3 not belonging to x intersection gm2 also. So in this way I have a sequence, this x1, x2, x3, and continuing like this, I will have a sequence xn. We will have a sequence xn such that your xn belong to x intersection gmn, but xn does not belong to intersection of all those x intersections gmj's where j is varying from 1 to n minus 1. So we have constructed a sequence xn in this fashion, and now I will show that this sequence xn is having no convergent subsequence, and in fact we will show that no point of x, the topological space, no point of x is a cluster point for this sequence. If there is no cluster point, definitely there will be no convergent subsequence, because the point where the convergent subsequence converges is known as cluster point. If there is no cluster point, that means no sequence is converging to some point, that means it has no convergent subsequence. So we will show that no point of x is a cluster point. So let x belonging to x be an arbitrary point, and we will show that this x, small x, this is not a cluster point since x belongs to x. And what is x? X is union of all gns where n belonging to n, as the collection of all gns was the countable open cover for x. So x is equal to union of this, and x belonging to x means x belongs to this, and if x is belonging to this union, definitely x will belong to some member of this collection. So definitely this means x belong to GP for some p belonging to the set of natural numbers. Now x belongs to GP and x belongs to x. That means x intersection with this GP is not phi. And from the starting, those sets which are having non-empty intersection with x, we have named them as GMIs, GM1, GM2, GM3 and so on. So this GP must also be of that type. So there will be some MQ. So there, or you can say, therefore there exists some Q belonging to the set of natural numbers such that your GP is GMQ. So GP will be equal to some GMQ. And if I is greater than Q, then our way of construction of the sequence xn shows that this xi does not belong to GMQ. That means there, after some stage, there will be not the condition that all the members of the sequence will belong to GMQ. That means GMQ is open set containing x, and it does not contain all the members of the sequence after some stage. And it shows that x is not a cluster point. And what was x? X was an arbitrary point. So that means no point of this topological space x is a cluster point for this sequence xn. That means this sequence xn is having no convergent subsequence, which is a contradiction, because we have supposed that it is a sequentially compact space. And if it is a sequentially compact space, then every sequence must have a convergent subsequence. and here we are having a sequence xn having no convergent subsequence, so it is a contradiction, and this contradiction arrived because our supposition was wrong, and what we have supposed that this topological space is not countably compact, so our supposition was wrong, hence this topological space x tau must be countably compact. So what we have shown that every sequentially compact space is countably compact. This we have shown. And earlier in the previous video we have shown that every countably compact topological space is compact. So there is a chain. If a topological space is sequentially compact, then it is countably compact. If it is countably compact, then it is compact. So indirectly you can say that every sequentially compact topological space is also a compact topological space. So this theorem may also be asked in your examination, that prove that every sequentially compact topological space is compact. So the proof will be in two ways, from sequentially compact to countably compact, and from countably compact to compact. So with this theorem, with the completion of this theorem, I am going to stop this video here. In the next video we will have more theorems on sequentially compactness, and then we will move on to the topic of locally compactness. Till then, thank you once again.